Algebra 3 Trig, Chapter 4, Section 3, Conics. Now, before you dive into this, I do suggest that you go to mathisfun.com, and there was an overview of what we're talking about. You can search for conics using this website. You can, I believe the link will actually work, and if you click on the link here, it will take you to the page on conics, and it'll just give you an overview. So you can have a preview of what we're doing. We've already looked at circles and parabolas algebraically. We did equations of the circles. We've done equations for parabolas. And now we're going to look at them from a more geometric point of view. We're going to define them by their relationships to major points and lines, and we're going to develop equations for those relationships. Now, we did this in Algebra 2, so there should be some background there. You should kind of remember this a little bit. We're going to delve a little bit deeper and get more into it than we did last year, but hopefully some of this will seem very familiar. First, we're going to talk about parabolas, and you'll notice in the upper right corner there I have a graphic that shows why this is called a conic section. If you take two cones, and they're point to point like here, and you were to slice them with a plane where the plane went through one of the cones at a slant, then that cutout section you see there that's darker is going to be in the shape of a parabola. So that is why a parabola is called a conic section. Now, we've learned that f of x equals ax squared plus bx plus c is the general form for the equation of a parabola that opens either up or down. We're now going to give a general definition that is independent of the direction that it opens. So, parabola, here's the definition. It's the set of all points in a plane that is the same distance from a fixed line called the directrix and a fixed point called the focus. The axis of the parabola is the line drawn through the focus perpendicular to the directrix, and the vertex is halfway between the focus and the directrix on the axis. I'm going to show you what this looks like. So there's my parabola, and you see the focus and you see the directrix. And the idea is that you could pick any point on that parabola and measure the distance from that point to the focus, and then measure the distance from that point straight perpendicular to the directrix, and those two distances would be the same thing. So the focus and the directrix, neither of those lie on the parabola itself. The vertex, which remember is the turning point of the parabola, is exactly halfway in between the point and the line. And then the axis of symmetry, which we've talked about before, runs through the focus and through the vertex, and it is perpendicular to the directrix. Okay, continuing on with parabolas, the standard equation of a parabola with a vertex at the origin is, well, for a parabola that opens either up or down, the equation is x squared equals 4py. The directrix is the line y equals p or negative p. P is the distance. Actually, a better way of looking at it is p is the distance from either the directrix to the vertex or the focus to the vertex. So it's one of those two distances. When it opens up like this, then it is going to be positive, and when it opens down, it's going to be negative. Now, for a parabola that opens to the side, you'll notice the formula is similar, but instead of x squared equals 4py, we have y squared equals 4px. And the good news is that p is really the same idea. It's still the distance from either the vertex to the focus or from the vertex to the directrix. Or another way of looking at it, it's half the distance from the focus to the directrix. It's the same thing for both situations. Now, the good news is that you will be given a formula sheet for this, if I haven't given it to you already, and you will be able to use that formula sheet on any tests and quizzes that we take in this chapter, and then if any of this appears on the final exam, you'll be allowed to use the formulas for that as well. So the main thing that you need to be concerned about as we go through these is knowing which formula to use and understanding what the letters stand for. Because if you don't understand, knowing that it's y squared equals 4px is great, but if you don't know what p represents, then it's not going to do you much good. So you need to be able to determine which equation do I use and what do the various letters stand for. Other than that, you will be given the equation and be able to work with it from there. Just some applications of parabolas. The conic sections are extremely useful. They're used in all forms of sciences. They're used in architecture. Parabola is a very sturdy structure. That's why it's used in architecture a lot. The first picture you see is the Roman aqueducts. And you can see that the arches are used, the parabolas are used as arches to support the structure. So the picture in the top middle there is pretty famous. That's the St. Louis Arch. A satellite dish is parabolic. And the reason for that is that it has a unique property. If anything that hits the curve itself will be reflected to the focus, or anything coming from the focus and hitting the curve will be reflected in perpendicular lines. And this makes a parabola a very great shape to use for things like satellite dishes, speakers. If you look at a flashlight, I mean the older flashlights that have the light bulb with the silver pan behind them, those silver reflectors behind them are parabolic because it allows the light beam to be focused in a straight line instead of just light being scattered everywhere. So very useful shape. They also use parabola, in order to simulate zero G, so weightlessness. What they do is they take a plane and they go up and they go at a very steep angle, and then they curve up and come back down, and what that does is that it will simulate weightlessness, and the trajectory that the plane uses, or that they use to fly the plane, is a parabolic arc. If you've had physics, and I think most of you are probably in the middle of physics, or if you've ever done any shooting, then you should know that a projectile, the path of a projectile, is a parabola. So you're going to see parabolas a lot just all around you. It's a very, very useful shape. All right, let's try some examples with a parabola. Now you're going to find the focus and the directrix. You're going to want to use the formula. Make the equation look like the formula first, and then you're going to sketch the parabola. And I'll tell you what, pause the recording and give this a try. See if you can do it on your own, and then resume and see how you did. Okay, the first thing I did is I said I solved for x squared because my formula is in the form x squared equals 4py. And so that gave me x squared equals 2y. Well, what that means is that 2 must be 4p. So if 2 is 4p, you're going to solve for p and you get 1/2. Okay, that means that from the vertex to my focus is 1/2, and from my vertex to my directrix is 1/2. This is a positive equation, so it's going to open up, which means my focus is going to be above my directrix. So I plot the focus and the directrix. And for this section, the parabolas, the vertices are always going to be at 0, 0. So we're getting a lot of practice in with the vertices being at 0, 0. In the next section, we will move it away from 0, 0, and it'll be a little bit more involved. But this is what the parabola should look like. Okay, here we have a similar problem. This time we've got y squared equals negative 6x. Again, I suggest that you compare it to the formula, y squared equals 4px. Pause the recording, give this a try, and resume to check your answer. Okay, if y squared equals 4px, then negative 6 must be 4p. So if you say negative 6 equals 4p and you solve for p, you get negative 3/2, which means my focus is at negative 3/2, 0. Excuse me, and my directrix is at x equals 3/2. This is going to open to the left. Just remember, a negative equation for a parabola means it's either going to open to the left or open down, which it kind of makes sense. It's kind of intuitive. You would expect a negative to go toward the left. You would expect a negative to go down. So it actually kind of makes sense, which is nice. So it is opening to the left. We place our focus at negative 3/2, and our directrix at positive 3/2, and then the parabola you try to draw so that it's in between both. Now you're going to find the standard form of the equation of the parabola with the given characteristics and the vertex at the origin. Now, what I suggest you do, even though it doesn't say you have to sketch it, what I do for these is I actually make a sketch. I will draw an XY axis. I remind myself that the vertex is 0, 0, and I place that on there. And then I place the focus. Once I know where the focus is, I know where the directrix is because it's exactly on the opposite side of the vertex. It tells me a bunch of stuff. It tells me what P is, and it tells me the direction that it opens. And I need to know what direction it opens to know if it's going to be x squared or y squared. Pause the recording, give it a try, and resume to check your answer. Okay, so this equation, if you place the focus and everything like I told you to, you'll realize that this opens to the left. So it is going to be a y squared. And the distance between the vertex and the focus is -2. So P is -2. So we have y squared equals 4 times -2x, or y squared equals -8x. All right, same type of problem. This time they are giving us a point that it passes through, and they're giving us the that it has a horizontal axis. The fact that it has a horizontal axis tells me it is going to open to either the left or the right. Now you actually have 2 points because you know it passes through 4, 6, and you know the vertex is at the origin. All right, pause the recording. We've actually done problems similar to this earlier this year with circles and parabolas. So pause the recording, give this a try, and resume to check your answer. Okay, the horizontal axis tells me my equation is y squared equals 4px. The problem is I don't know p, but what I do know is that it goes through the point 4, 6. So I substitute 4 for x and 6 for y, and I solve for p. And I get that p is 9/4. So I go back to my original equation, y squared equals 4px. I replace p with 9/4, and I simplify and get y squared equals 9x. All right, let's talk about an ellipse for a minute. And you'll notice from the graphic, we've got the plane intersecting the cone. Now with the parabola, the plane went through the bottom of the cone. With an ellipse, it just slices through but does not connect with the bottom. So we end up with an oval for a cross section. The definition of an ellipse is a set of all points in a plane, the sum of whose distance from 2 distinct fixed points called the foci is always the same. We have several parts here. We have the major axis, which is the line through the foci. It's also the longer of the 2 axes, so it's on the longer part of the oval. AB is going to be our major axis here. The center is halfway between the foci on the major axis. The F1 and F2, by the way, in this diagram are the foci. Foci is plural for focus. And halfway in between them is the center. The minor axis is the shorter of the 2 axes, and that is CD. And it goes through the center as well. And then the vertices are the points where the ellipse touches the major axis. So A and B are going to be our vertices. You'll notice we've got some other labels here. The little a is always going to be the distance from the center to the edge of the major axis. The B is going to be the distance from the center to the edge of the minor axis. And it's not labeled here, but C will be the distance from the center to the focal points, one of the focal points. The standard equation for an ellipse centered at the origin is x squared over a squared plus y squared over b squared equals 1. Now this is for an ellipse where the long axis is your x-axis or is the horizontal axis, or x squared over b squared plus y squared over a squared equals 1. And this is where your long axis is the y-axis. The major axis length is 2a, and the minor axis length is 2b. So a is center to the end of the major, as I said, and b is the center to the end of the minor axis. The foci are c units away from the center. So center to foci would be c, and we have an equation that relates a, b, and c, and that equation is c squared equals a squared minus b squared. Applications of an ellipse. The first picture you see there is the rotunda in the Capitol building in Washington, D.C. Now, just like a parabola had an interesting property where anything coming from the focus that hits the parabola reflects in a straight line, ellipses have interesting properties too. And one of the properties that was discovered is that anything that is coming from one focus and hits the side of the ellipse will be reflected to the other focus. And a long time ago it was discovered that in the rotunda, if one person is standing at one of the focal points of the ellipse and another person is standing at the other, that you can speak very quietly and be heard at the other focus. And this was actually, at least according to legend, used by some politicians to hear what other people were talking about and get what was going on around them. So anyway, the rotunda in the Capitol building, not the White House, the Capitol building in DC is elliptical. The second picture you see there is the orbits of the planet are elliptical. And of course, who can forget the bat symbol, which, I guess doesn't have any special properties other than summoning Batman, but it is an ellipse. And then footballs as well are also elliptical. So let's do some examples. You're going to write the standard form of the equation of the ellipse with the given characteristics and the center at the origin. Again, I strongly suggest that you make yourself a little sketch. You know the center is 0, 0. Here you know that the vertices are going to be at 5 and -5, and the vertices are where the ellipse connects with the longer axis. So that tells you a little bit about the equation, and then you've got the focal points. Remember, you're going to have to use the equation that relates the focal points, or C, to A and B. Pause the recording, give this a try, and resume to check your answer. Okay, so A has to be 5 because our vertices are at 5 and -5. And the focal points are at 2, -2, so C is 2. We use the equation that relates A, B, and C to solve for B, and we get that B is the square root of 21. So x squared over a squared plus y squared over b squared equals 1. Fill in the numbers, and we're done. Okay, another problem. This time they gave us the vertices, and they told us that it has a vertical major axis, which actually knowing the vertices tells us that, and it gives us a point that it passes through. This is going to be similar to the parabola problem we did. So pause the recording. You might want to make a sketch. Give this a try and resume to check your answer. Okay, so we know that A is 5, and that gives us x squared over b squared plus y squared over 25 equals 1. We need to find b. Well, we know it passes through 4, 2. So replace x and y with 4 and 2 and solve for b. And we get that b is 400 over 21, or b squared is 400 over 21. And what they did, you would have x squared over 400 over 21, which is kind of awkward. You don't really want to do that. So what you do to actually get it to look like this is you say, okay, that means x squared divided by 400 over 21. But when you divide by a fraction, you keep change flip. So that gives you x squared times 21 over 400, which is what you see here, 21x squared over 400. Of course, if you understand that relationship, it's just a really quick, easy fix. All you do is take the denominator of the b squared and put it on top. Okay, now find the vertices of the ellipse and sketch. Now this shouldn't be too bad, so pause the recording, give it a try, and resume to check your answer. Okay, so we know that by sketching it, we know that A is 5/3 and B is 4/3. You need to take the square root of what's under the x squared and what's under the y squared. The bigger number is always going to be your major axis. And what it's under tells you which axis is the major axis. The center is at 0, 0, so just place A and B and draw your ellipse. This one's a little tough because you need to make it look like the equation. And to do that, the equation is supposed to be x squared over a squared plus y squared over b squared equals 1. Now the y squared you can put over 1, that's fine. But we need to find a way to express 4x squared as x squared over something. Think about a moment, Pause the recording, see if you can figure out what to do, and then resume to check your answer. Okay, so really quick trick. What you do, it's kind of like the reverse of the trick we did a minute ago with the 400 over 21. What you do is you take the 4 and you say, okay, well, multiplying by 4 is like dividing by 1/4 because you would do keep, change, flip. So it's x squared over 1/4 plus y squared equals 1. So a is always the bigger number. A is 1. B is 1/2. Remember, you take the square root of those denominators. We know that y is going to be our major axis because the 1, the bigger number, was under y. The center's at 0, 0. So plot A and B and draw your ellipse. Okay, now let's talk about parabolas for a minute. If you look at the graphic, a parabola is what you get when you slice the two cones. It's completely through both of them. It looks like two parabolas set back to back. The definition is the set of all points in a plane where the absolute value of the differences of the distances from two fixed distinct points, called the foci, remains the same. Now, we have a transverse axis. That's the line that goes through the graph, through the focal points, through the vertices. It actually connects with the graph. Probably an easy way to remember that is trans means across or through. So the transverse axis goes through the actual graph itself. And we have the center. The center is halfway between the vertices or the foci on the transverse axis. So we've got 5 points that are all going to line up on that axis. We have 2 focal points, we have 2 vertices, and we have the center, and they're all going to line up on the transverse axis. The vertices are where the branches, which are the 2 parts of the graph, where they connect with the transverse axis. The conjugate axis is the line perpendicular to the transverse axis. It's the one in red there. It's through the center of the hyperbola. Now, if you're looking at this, you may kind of recall doing the box and the diagonals, and we'll talk about that. For a hyperbola centered at the origin, it's very similar to an ellipse. The difference is you have a minus instead of a plus. That's one of the differences. The other difference you'll see in a minute. But again, here's the thing. A is going to be the distance from the center to where the hyperbola connects on the transverse major axis. B does not have such an easy definition. C is going to be the distance from the center to the focus. Okay, and we have an equation that relates A, B, and C. B squared equals C squared minus A squared, or you could say that C squared equals A squared plus B squared. Both of those are acceptable. When the hyperbola opens up and down, the equation looks slightly different. The y squared comes first. So with this, we actually do reverse the x and the y. The axis that it goes through will always come first. Again, A squared is the center to the vertex, or A is, not A squared, and B is the, well, B isn't. B we'll talk about in a minute. C is the distance from the center to the focus. Now, you'll also notice I've got some equations there in red. Y equals negative A over BX, and Y equals A over BX, and there's for the other one too. What those are the equations of those 2 diagonal lines. There's a couple of ways you can come up with those 2 diagonal lines. We talked about making a box. If you remember how to make the box, what you do is 2 of the sides of the box are formed by the vertices. The other 2 are by B. So you plot B, the distance from the center to B, on the conjugate axis, and those are the other 2 sides of the box. You make a box with them, and then you draw the diagonals through the box. The equations for those diagonals are what you see here. It's either, if it opens left, right, it's y equals negative b over a, and if it opens, or y equals b over a, actually it's both. If it opens up down, you just flip that upside down. It's y equals negative a over b, or y equals a over b. Now, an easy way to remember it, it's always what's under the y, the square root of that, over what's under the x, the square root of that. So for the horizontal, it's b over a. For the vertical, it's a over b. Okay, so here we have a graph of a hyperbola, and you'll notice that the 2 branches are separated by 2 crossing asymptotes, as we said before. To find them, you're going to draw a rectangle with sides going through the vertices and the points that are B units away from the center. So that's where the B comes in. The diagonals of that rectangle are asymptotes. And we did this last year, so hopefully you remember that. The equations are y equals plus or minus b over a if it's horizontal, and y equals plus or minus a over b if it's vertical. Here's some applications. A little harder to find the hyperbola ones, but what you have, the first picture there is a jet going supersonic. And then let's see, we've got actually the top and the bottom there, that's illustration of that. There are comets that have hyperbolic orbits. The nuclear reactor there is kind of a hyperbola shape, and then of course the basketball design there. So, some examples, same type of thing we've been doing. Find the standard equation, form of the equation with the given characteristics and centered at the origin. Again, good idea to make a sketch, but that's up to you. Pause the recording, give it a try, and resume to check your answer. Okay, my vertices are at 1, 0, so A is 1. My asymptote is 3 over x, so the horizontal transverse axis, what that tells me, remember, the equation for the asymptote, since my axis is horizontal, is going to be b over a. So 3 equals b over a, and I already know a is 1, so b must be 3. So I'm going to put those into place in the equation, and I have x squared over 1 minus y squared over 9 equals 1. Write the standard equation of this hyperbola. Again, sketches help, so pause the recording, give it a try, and resume to check your answer. Okay, they gave me my vertices, so I know A is 3. I also know that that's going to go under y, and y is going to come first. So I have y squared over 9 minus x squared over b squared equals 1. The other piece of information I have is a point on the graph, so substitute that point in for x and y, and solve for b squared, and then you have your final equation. Y squared over 9 minus x squared over 9/4 equals 1. Okay, find the vertices and sketch with the asymptotes. Pause the recording, give it a try, and resume to check your answer. This one would either be incredibly tricky or incredibly easy. A and B are both 1. Now for an ellipse, A and B will never be the same. A will always be larger. But for a hyperbola, they could be the same. A could be larger, A could be smaller. It's a different situation. So for this one, A and B are both 1. So since x comes first, we know that it's going to cross the x-axis. So we plot that. We plot our center. And we can do our couple things to do our asymptotes. The equation is going to be, excuse me, the equation is going to be plus or minus b over a, which is 1 over 1, x, so it's just going to be plus or minus x. You can also draw the rectangle and do the diagonals from there. Okay, same type of problem. Now this is going to be similar to what we did with the ellipse. Really the only difference is that we had 4x squared before, we have 4y squared now. Pause the recording, give it a try, and resume to check your answer. All right, we're going to pull the same trick we did with the ellipse. The 4y squared is going to become y squared over 1/4, and the x squared will be over 1. Since y squared is first, it's going to cross the y-axis, and the square root of 1/4 is going to be a. The square root of 1 will be b. I know my center's at 0, 0, so I know my vertices. I can plot those. I also know a and b, so I can draw my rectangle and diagonals. I can also calculate the asymptotes, which, since this is opening up and down, my asymptotes are going to be plus or minus a over bx. So a over b would be 1/2 over 1, which is 1/2, so plus or minus 1/2 x.